Modern large language models can synthesize complex code and pass professional bar exams, yet they are buckling under their own structural weight. To reach these performance levels, they require ever-expanding architectures that consume massive amounts of power and compute. The root of this inefficiency lies in how these systems process information. When you feed data into an LLM, the raw text is segregated. Tokens are translated into representations called embeddings, which are then processed by an entirely separate mechanism, a massive matrix of private weights. Every single time an input moves through this pipeline, the system burns compute translating between these incompatible structural languages. Information, representation, and operation are all forced into isolated silos. And once the model finally learns a relationship, that knowledge is trapped. It gets encoded as millions of non-transferable decimal approximations, locked entirely inside a private matrix. The Aurora architecture proposes a different path. It operates on the thesis that artificial intelligence doesn't require continuous probability distributions. Instead, intelligence can be constructed from structures that are discrete, strictly verifiable, and entirely compositional. To achieve genuine computational efficiency, we have to stop scaling up the parameter trap. We need to rebuild the mechanics of machine learning from the absolute lowest level of logic. For the last decade, the default strategy for advancing AI has been to build increasingly massive compute clusters. But the foundational proofs of information theory took the opposite approach. Claude Shannon proved that highly complex information could be perfectly quantified and represented through the most minimal, discrete choices available. Aurora takes that minimalist philosophy and applies it directly to modern machine learning. The goal is to discover a single elemental operator that is capable of building every part of a thinking machine. Architectural elegance is found by stripping away massive arrays of decimal weights and isolating the minimum viable unit of logic that can scale infinitely. The first step in that reduction is discarding floating-point real numbers entirely. Aurora replaces them with a discrete base 3 logic unit, the trit. In this ternary system, state 0 provides determination in one direction, and state 1 provides determination in the complementary direction. The crucial innovation is the third state. State 2 represents a relationship that is entirely open, indeterminate, or outside the computational space. In a standard neural network, the system has to approximate what it doesn't know by crunching through highly intensive, continuous decimal mathematics. Aurora sidesteps this computation. By assigning a distinct state to uncertainty, openness becomes an explicit word in the machine's vocabulary. The system doesn't need to mathematically estimate an unknown, it simply flags it as structurally open. Removing continuous matrices reduces the total number of floating-point multiplications required to process an input. The architecture structurally defines its own blind spots, instead of using complex mathematical estimation to guess at them. To process these trits, Aurora employs a single universal operator known as the Trigate. Modern hardware relies on specialized instruction sets. GPUs use different physical mechanisms to multiply matrices, route data, and store memory. Aurora eliminates this fragmentation. The exact same Trigate operator is reused at every level, scaling fractally to build the network. Whether the system relates discrete values, detecting internal contradictions, synthesizing structural concepts, or governing its own memory recall, it relies on this identical mechanism. Functional diversity here is achieved without writing new underlying code or designing specialized chips. The behavior of the machine emerges entirely from how this one elemental gate is positioned and composed. We can see the efficiency of this uniformity by looking at natural human language. When we speak, our brains don't rely on completely different physiological structures to process a word acting as data versus a command. A single word can serve as a static object, describe a relationship, or issue a direct instruction. Its function is dictated entirely by its context within a sentence. Aurora applies this exact principle through a property called homoiconicity. Data, knowledge, operations, and control mechanisms are all expressed using the exact same ternary tensor structure. Because the representation of an input is structurally identical to the rule transforming it, there are no tokens to translate and no separate weight matrices to consult. Homoiconicity bridges the divide between the information being processed and the machine processing it. The system handles data natively without ever needing an independent translation layer. This structural unity dictates how the system acquires knowledge. Standard models rely on global backpropagation, tweaking millions of parameters simultaneously just to integrate a single new fact. Aurora replaces massive global recalculation with a continuous local learning model driven by the F field. When the system encounters uncertainty, the F field creates a localized pressure gradient around the open relationship, directing modifications to the surrounding operands. It physically aligns the open states until the relationship finds absolute mathematical consistency and locks together. Once closure is achieved, it is synthesized into a discrete, reusable unit called a complex tensor. These closed tensors are stored directly in the node's local dictionary. If the machine encounters that exact same relationship again, it doesn't calculate anything. It just pulls the completed tensor from the dictionary. Learning is no longer a process of blindly shifting probability weights until the error rate drops. It is the permanent closure of an open relation, guaranteeing that the machine expends zero compute on that specific problem ever again. The implications of this architecture scale rapidly when we zoom out from a single node to a fully distributed network. If a standard language model learns something valuable, you cannot easily extract the precise synaptic weights responsible for that insight and graft them onto a different model. Transferring knowledge requires intense, expensive retraining. Aurora allows for direct structural exchange. Because its knowledge is stored as canonical, discrete tensors instead of private probabilities, a breakthrough in one location can be immediately transmitted across the network. The receiving node doesn't have to train on new data. It directly integrates the shared complex tensor right into its own local dictionary. And because the tensor is structurally complete, the receiving node can instantly verify its accuracy through a simple, low-cost re-execution of the logic. The total compute required by the network decreases with every shared discovery. The moment a single node achieves structural closure on a problem, every other connected node is immediately spared the energy of having to learn that same relation independently. The path to sustainable artificial intelligence is not found by endlessly scaling up probabilistic math, but by building discrete systems that never have to relearn what the network has already comprehended.